Alrighty. So, let's go to our notes here and talk about, or kind of review some of the stuff we covered yesterday, right? So, yesterday, we introduced the idea of finding the area in polar graphs, right? Or area of a polar graph. And so we started with the idea that, well, when we were doing rectangular coordinates, right, we were using rectangles, right? X and Y lent themselves to using an infinite number of rectangles to add up, right, infinite number of infinitesimally thin rectangles to create the area underneath of a curve, right? And since the area formula for a rectangle is so simple, it's just length times width, when we ended up finding the area under a curve, then we just took the length of those rectangles, the length being like their height, you know, we could call that, and that would be the function that determines the height of the rectangle, and then times dx, right, that width there is that teeny little change in x that creates, you know, the width of the rectangle. In polar, though, we're not moving, you know, left and right. We're not accumulating area from left to right. Instead, in polar, we are like kind of like sweeping out the area from our polar axis, sweeping through the angle theta and accumulating area in that sense. That kind of shape that we create then that we use is a wedge, right, or a sector, more officially, a sector of a circle. And we're going to add up an infinite number of these like teeny tiny wedges to then create the area of the polar graph. Okay, and so that's why the formula has to change here too. We're no longer using rectangles, so it's not just length times width. We're using the theta over 2 pi times pi r squared, or as we simplified it to be 1/2 theta f of theta squared. Okay, and that's why when we integrate, we have to integrate this right here, the 1/2 f of theta quantity squared, and then d theta for that teeny little change in theta to create all those, you know, little angles right there, right? All these little things here. All these are that little theta. Okay, little d thetas there. And they're all the same. Okay? So anyway, that accumulation of those sectors creates the area for our polar graph. Okay? From theta equals A, right? Instead of like going left to right, instead we were going from the pole, we sweep from the pole and we accumulate all these sectors like that, okay? And so we go from A to B, right? We stop at the B there. All right. So we did our first area, all right? We identified our function r here. That's pretty much the easy part, right, is identifying what r is. It's more like trying to figure out what those limits of integration are, right? And so we use, you know, the fact here that we wanted to find the area enclosed by 2 sine theta, and so we created, you know, we kind of drew the graph to help us out. That can be a good idea to do. Okay, and saw that rotating from theta equals 0 to theta equals pi gives us that graph. And so then we could just integrate from 0 to pi and go from there. Okay. Of course, sine squared, right, that was where we also had to identify sine squared. We can't integrate that, right, as it's written. We have to use our identity here. Sine squared equals 1/2 minus 1/2 cosine 2 theta. And then that allows us to integrate using a u substitution, of course, for that 2 theta there. Okay. Here, same thing. You're right. Again, just figuring out the limits of integration. The function r itself, not too bad. It's those limits of integration that are pretty tricky. Okay. Same thing here. We took something that looks like a rectangular graph, right? That looks like something we would have seen before. We had a line and maybe like a quadratic or something. But in fact, these were polar curves, and so we had to, you know, adjust our thinking a little bit there. And we put things in terms of k. Number 4, I wanted to talk about just real quick. I wanted to highlight one thing just to make sure that we're okay with this. So this was a non-calculator problem, okay? And again, what I typically have you guys do when we go through this, right, that typically we want to just be comfortable using like our quadrant angle. So like 0, pi over 2, 3 pi over 2, 0, pi over 2, pi, 3 pi over 2, and I guess 2 pi as well, okay? So we found our starting point was here when theta was equal to 0, right? We found that by just plugging 0 in for theta, solving for r, and we got r equals -1, so that's this point, okay? And then when we jump to pi over 2, when you plug pi over 2 in here, cosine of pi over 2 is 0, times 2 is still 0, and then 1 minus 0 is 1. So at pi over 2, we get to this point. So we go from theta equals 0 to theta equals pi over 2, all right? And we know then, from 0 to pi over 2, we go from an r value of -1 to 1, which means we have to go through an r value of 0. So we know we have to go through the pole there, right? And that would be our next limit of integration, right? 0 is where the curve starts, but then our next limit of integration is going to be right here. How do we find that, right? So I kind of yesterday, I guess, showed it by guessing and checking, but I mean, if we wanted to see when our r value was 0, we can take our curve, and actually calculate when that r value is 0 by just taking our curve and setting it equal to 0, right? So just to make sure you guys are okay with that. And so then we get theta, 1/2 equals cosine of theta. Okay, and so when does the cosine of theta equal 1/2? Well, the first time it happens, the theta between 0 and pi over 2 that we're looking for is pi over 3. Okay, I mean, technically also, right, we could say, 5 pi over 3 as well. But we don't want that one because it's not between the 0 and the pi over 2 there. Okay, and so that's another way you can actually calculate the pi over 3 if you need to set it equal to 0 and stuff. All right, so there's that. Any questions on anything we did from yesterday? We're all still good. I didn't further confuse things. Okay, or you're just so confused you want to just move on with things. So we'll do that. All right, so moving on here. All right, example 5 asks us to find the area in the inner loop of r equals 2 minus 4 sine of theta. So let's maybe get an idea here, right? So we're finding the area. So first, I don't need to put a 1 there. Let's first, set up our area formula. So integral from a to b of r squared d theta. Okay, what is our r in this scenario? Yeah, 2 minus 4 sine theta, right? It's like the curve right there. So that's the easy part, right? So we have the 1/2. It's these limits of integration. That's the tricky part. We got to try and figure out what our thetas are. Where do we start and where do we stop with our thetas? Okay. So we've got our setup here, but now let's go to our graph. All right, it's nicely, conveniently provided for us here. And we'll make a little table again just to kind of get an idea about what's going on. And again, I'm going to do 0, pi over 2, pi, 3 pi over 2, and I guess I can do a 2 pi, but I mean, we understand that 2 pi and 0 are going to be the same coordinate there. All right, so we'll plug in. Sine of 0 is 0, times 4 is 0, and then 2 minus 0 is 2. Sine of pi over 2 is 1, times negative 4 is negative 4, 2 minus 4 is negative 2. Sine of pi is 0, times 4 will still be 0, so we get 2, and then 3 pi over 2, sine of 3 pi over 2 is going to be negative 1 times negative 4 is positive 4, plus 2 will make 6, and then 2 pi, well, it's the same as 0, so it'll be a 2 again. Okay. So again, it's important that we are not only able to graph, but we want to be able to graph, I want to use the word quickly, or maybe like efficiently is a better word to use it. Bless you, okay? We don't want to sit there and have to do like a bunch of, points to really figure things out. So let's see if we can just figure this out based off of the table that we've got, right? So we've got the point theta equals 0, so at angle 0 on the polar axis here, we're going to go out 2. Okay? And then the next angle, pi over 2, so that's this, pi over 2 is in this direction. It's a negative 2 r value. So that means we're going to go, instead of towards the pi over 2, we're going to go 2 away in this direction. Okay? So now, this is a little bit funky, right? Because we have to go from this point, we have to connect to this point. And that means we're going from an r value of 2 to an r value of negative 2. Well, what r values, by the intermediate value theorem, right, what r values do we have to hit, given that we started on r value of 2 and we have to go to an r value of negative 2? What r values do we have to hit? We got to hit 0. We got to hit negative 1. We got to hit positive 1. So we're going to hit all the r values between these two. So that means we're going to go from our positive 2 through 0 to negative 2. That means if we go through an r value of 0, that means we're going through what point? The origin, or the pole there. Exactly right. And so it's going to look something, like this. And then we have, so there's me going through the origin, right? But then I got to circle back around here. I got to get to this point. So I got to have to go like that. Got to go through the pole. We're going from an r value of 2 to negative 2. We're going through 0. So we got to go through the pole. We know that's a point. We're not really sure for what angle theta that is. We could figure it out if we wanted to, but then we can continue on through and then just get to that point. And so now our next point is then pi 2. So again, an angle of pi is this direction. It's a positive r value 2, so we're going to go 2 out. And so that means I got to connect from this point to this point. Okay? And we're going from an r value of -2 to an r value of +2. So that means we have to go through the pole again, right? So we're going to go back to the pole. And again, using the symmetry here to help us out. We're like, oh, okay, there it is. Okay, it's kind of symmetric to itself there. I didn't do a very good job making it symmetric, but it is. Okay, now is the pi over 2. Now we're going to do the 3 pi over 2 is 6. So 3 pi over 2 is this angle right here. And we'll go out 6 towards it. 1, 2, 3, 4, 5. We'll make a 6. Okay, so that's our next point is right down there. And so we're going to circle around to that. Okay. And then 2 pi 2, well, we're back to where we started. So there's our full shape right there. Okay, so our graph, the thing that we're trying to find the area of is this piece right here. Right? This piece right, or I like to draw it. I like to have kind of like my sketches like radiate out from the pole there. Okay? So, what are our limits of integration going to be? Well, we started at 0 and then we went to pi over 2. To go from 0 through to that pi over 2 there, right, we had to cross through the pole. So a 0, right, it's going to be in here. One of our angles is going to be between these two because that's where we go through 0. And then likewise, another 0 is going to be between these two because we go from -2 to +2. Right? So when does r equal 0? Right? Well, we'll set 0 equal to 2 minus 4 sine of theta. Okay, and so we get 4 sine theta equals 2, and so sine of theta equals 1/2. Okay, when does sine of theta, excuse me, equal 1/2? Oh, over this way?
Yeah.
Okay. Pi over 6 and 5 pi over 6. Exactly right. And pi over 6 is between 0 and pi over 2. 5 pi over 6 is between pi over 2 and pi. So those are our two limits of integration. Okay? At pi over 6, we start at the pole. We start to create this inner loop. Then we go through pi over 2. And then we finish here at 5 pi over 6 back at the pole. And so that creates that little inner loop there. So we're integrating from the pi over 6 where it starts to the 5 pi over 6 where it completes. Okay. Now, I was talking about symmetry before, right? And I showed you kind of in the homework, right? This object here, right? This polar graph, it's symmetric about, I guess, the y-axis, okay? And so what we can do here is instead of doing the full angles from pi over 6 around to the 5 pi over 6, we could alternatively describe this as 1/2 the integral. Let's go from pi over 6 to, what was this theta value down here? Pi over 2. Yeah, so we could alternatively say pi over 6 to pi over 2 of that same curve, 2 minus 4 sine of theta squared d theta. That would give us then this half right here. And then what should we do with this integral to get then the full loop? Yeah, just double it. Okay. So you can do the full limits of integration here, pi over 6 to 5 pi over 6. That'll give you the full loop. Or you can do half the loop, pi over 6 to pi over 2, and then just double it using symmetry there. Yes?
Do you have to graph it and then say equal to 0, or can you just say r equal to 0 from the start?
So you can, that's a good question here. I think it depends on your comfort level, I guess, kind of thing. I like to graph it here for you guys just so we can see it and stuff like that. I think it's helpful to see it, maybe, but is it necessary? I don't think so. I don't think so, but I think it's helpful to just kind of see what's going on. Because again, when we say inner loop, it's like, okay, well, what's that looking like or something like that. So I think it's not a bad idea to do it. So yeah, Gabe.
How did you get pi over 2 again?
How do you get the pi over 2?
Yeah.
So because what I was shooting for here was to use symmetry. So that means I only want to come up with half of the area.
Yeah.
So it starts at pi over 6 right here, right? Just the same place we start. But then instead of going the full way around to get me the full area, I just want half. We'll go from pi over 6. Well, it goes down to this point. That would be that. And what is that? That point was when we had a theta of pi over 2. Okay. Right? Because at theta was pi over 2, we were at -2. So not this direction, down here. So that's why. Make sense? Yeah. So it's a lot to keep track of at once there, but this idea of symmetry can be helpful for us. Okay, so any other questions before we move into area between two curves? Very exciting. Okay, so number 6 then, find the area of the region inside the polar curve 4 equals 4, r equals 4 sine theta, and outside the polar curve r equals 2. So thankfully at least one of the curves, well, they're both not that terrible. But before we jump into area of the region between the two polar curves, let's refresh our memories a little bit. Okay, a little bit. Let's go a little bit back to the past here. And talk about area of a region between two curves and rectangular coordinates, right? So when we had something like f and a function g, right, two curves, right? They could create, regions between the two of them, okay? And we would identify where those two curves intersect, okay? And it's, again, the idea here, right? A and B are where G equals F, right? G is equal to F at A and B, so we would use those, points of integration. And so the integral here would be what? To find the area of this region right here, what would be the integral that we set up? The integral from what to what? A to B of, and then what do we integrate? F minus G, right. And it's important that we do it in that order, right? Because we want to do top curve minus the bottom curve. Okay? Top curve minus the bottom curve. Because the idea here, right, we do top curve minus bottom curve because we're trying to find the distance between these 2 points, right, for the height of our rectangle. The height of a rectangle is not determined just by a single function. It's determined by the combination here, the difference between these two. So we do top minus bottom. And this holds true even if your region was like below the x-axis. If your region was down here, you would still do the top curve, in this case, the one that's closer to the x-axis, and then the bottom curve minus the bottom curve, the one that's further from the x-axis, okay? But that's just because of the orientation with rectangular coordinates and stuff like that, okay? So that's what we did here, and guess what? We're going to do something very similar for polar coordinates, okay? So if you understand this concept, you'll be, much better off here for the polar stuff. So let's take a look then at our graph, right? Because this was very helpful to have a picture here. So let's take a look at our region as well, all right? So go ahead, take like a couple of seconds there and graph 4 sine theta and r equals 2. Okay, r equals 4 sine theta and r equals 2. Give it a shot, okay? And see if you can identify then what that region is between those two curves. So graph the two curves, take a couple seconds, like I said. See if you can identify the region. Okay, and I'll do that too. Let's see here. So, okay. So these two graphs create several regions, right? At least 3 I can identify here, right? So again, make sure you're identifying the region that is both inside 4 sine theta, but also outside the polar curve r equals 2. So inside r sine 4 sine theta, and then outside r equals 2. Okay. Okay. And so hopefully you got a graph that looks something like this. I went ahead and shaded the region in that we're using. Okay. So r equals 2, right? Easy enough to graph. That's like graphing, like a horizontal or vertical line in polar, kind of, that's like the, maybe the equivalent kind of thing, right? R equals 2 is just the circle. It's centered at the pole with r equals 2, radius 2. For sine theta, you have to do a little bit more calculations here, right? Sine of 0 is 0, so you start at the pole. But then when you do like sine of pi over 2, sine of pi over 2 gives you 1 times 4 would be 4. So you get this point, but you have to go from 0 to 4. So you're going to circle out like that around to it. And then at pi, sine of pi is also 0 again, times 4 would be 0. So at pi, you can bring it right back around to there. Okay, and so that creates then your shape. Yes?
So how do you know how far to go and like what pi values to use?
So again, my general recommendation for your theta values to use, you want to use your quadrants. 0, or like the angles that are in the, on the axes. So like 0, pi over 2, well, actually, it would be 0, pi over 2, 3 pi over 2, 2 pi, and then 3 pi over 2 kind of thing. Okay, that's what you want to use. If you need to, right, if you need to get more, for sine, we wouldn't use the pi over 6s, because sine of, if you need to for sine, we don't use the pi over 6s, because sine of pi over 6 is 1/2, or negative 1/2, depending on, which pi over 6 you're using. So that's easy to calculate, and you can do it that way. And that's what I did here, too, just to kind of convince myself that I did go further out. At pi over 6 here, you do get 2. At 5 pi over 6 here, you do get a negative 2, or a positive 2 as well. So that kind of deal. Make sense? Okay. Any other questions on this part right here? Okay. So for this one, right, we want to figure out then where do our curves intersect, right? We want to figure out our A value and our B value right here. Our curves do intersect. Okay. And so to figure that out, we're going to set for sine of theta equal to 2. Oops. So where do the curves intersect? Okay, so we'll set them equal to each other, and we'll solve. So we have sine of theta equals 1/2, and so when does sine of theta equal 1/2? Well, we were just talking about that, right? It's pi over 6 and 5 pi over 6. Okay? So that's where our curves intersect. And now we want to ask ourselves the question, from theta equals pi over 6 to theta equals 5 pi over 6, is a function always, okay? And so the question we want to be able to ask here, and this is here's where we're going to kind of differ a little bit from rectangular, right? In rectangular, it was top curve minus bottom curve. We were orienting ourselves about the x-axis, right? In polar coordinates, we orient ourselves always from the pole, okay? From that center of our rotation there. And so it's not talking about top minus bottom, okay? Although it does kind of work out that this way, it is top minus bottom, okay? But it's actually supposed to be outer minus inner, right? Just like we were talking about like washer method and stuff like that, and rotations there, right? It was the outer curve squared minus the inner curve squared. Same idea here. We're going to do the outer curve, take out the inner curve, and that will create our region there. So is a function always further from the pole? Okay, so again, outer versus inner, or further versus closer kind of thing. So is there a curve as we rotate from this pi over 6 around to the 5 pi over 6? Is there a single curve that's always further out than the other curve? And what is that curve? It's the 4 sine theta, yes. R equals 4 sine theta. Okay? Which, just like here, right, if our top curve changes, right, if the top and bottom curve switched, you'd have to write 2 different integrals. You have to write one integral where the one was the top curve and one was the bottom curve, and then the other integral where it flip-flops, right? We're going to see later that's going to happen for us too, where the outer curve is going to change, so we'll have to add another integral in. Okay, so for the area between 2 polar curves, it's the area of the further one minus the area of the closer one. Okay, we said that r equals 4 sine theta was the further of the 2, and so we're going to have 1/2 integral pi over 6 to 5 pi over 6 of 4 sine of theta, quantity squared d theta, minus, okay, because we're going to subtract then out that inner graph, which is also from pi over 6 to 5 pi over 6, of the inner curve, which is just 2. Squared, of course, d theta. You don't have to write it as 2 separate integrals, of course, since we're using the same limits of integration. We could write it as a single integral. So 1/2 pi over 6 to 5 pi over 6 of 4 sine of theta squared minus 2 squared d theta. Okay, like that. So that's putting it all together there. Now, let's say we wanted to use symmetry here. I would still need to start at pi over 6, but then what angle theta would I need to rotate to? My lower limit would still be pi over 6, but I would rotate up to what? Pi over 2, yeah, so I'll say or. So we'll say 1/2 integral from pi over 6 to pi over 2. Do my outer and inner curves change? No. So we'll still keep that 4 sine of theta squared minus the 2 squared d theta. But of course I'm going to then double that quantity, okay, using symmetry. In a case like this, right, the symmetry doesn't really save us any time, right, or any headache there, I would say. Like, it's like we kind of already have the 2 limits, so is it really that necessary? No, but it is helpful to have in some cases. Okay, so questions on any of that? And again, I can just kind of draw in here maybe to help out, right? We can see there's pi over 6, right? And there's that 5 pi over 6 as well. As you can see, again, that just that rotation from pi over 6 around to the 5 pi over 6, we accumulate. We start here, right? That outer curve stays outer, stays outer, stays outer, up into the 5 pi over 6. And that inner curve always stays on the inside there. Okay. You get that little crescent. It's a little croissant. Okay. Questions on any of that? Yes, Aubrey.
For the tests and stuff, is it all going to be like setting up instead of?
So, right, good question. Okay, so I'm for our purposes, just because I want to get through as many of these as we can today, kind of thing, we're gonna just set them up. But I will kind of I can talk you through here just real quick, right? Squaring a 2 is just going to give us 4, so integrating 4, no problem. Integrating 4 sine theta squared, well, squaring this would be 16 sine squared of theta, so that sine, you have a sine squared showing up, you need to use that exactly. So you have to use the conversion there of the 1/2 minus 1/2 cosine 2 theta, and then use like an integration, use substitution or something like that.
So we will have to solve.
You should be able to, yes. You should be able to, yes. Again, I think the review will give you a good idea about what will be expected for calculator versus non-calculator and stuff like that. So, but obviously you can't have a million of these because they take so long to set up in the first place, and then to also integrate by hand on top of it, it's just too much sometimes. But you should be able to do it should the question arise. Anywho, all right, find the area of the region inside the polar curve, r equals 4 cosine theta, and outside the polar curve, 2, r equals 2 cosine theta. So again, go ahead, draw it, okay? See if you can come up with a region here. So let's go ahead and sketch this. I'll give you a couple seconds there to do that. I'll do it myself.
Couple seconds.
All right, 30 or 60, or I don't know, whatever.
120.
120, you got it. But just because you asked, Mike.
Thank you.
You're welcome. Okay, so there's what our graph looks like with the region shaded in. Okay, question? Yep.
Like, why are you making it so, like, why? Like, so
Why?
fat, you know what I mean?
Oh, I see what you're saying. Well, because I am familiar with these kind of graphs, and I know they're going to be circles.
Gotcha.
Like and again, hopefully the idea is that you guys will become more familiar with these too. But a 4, when you have equal to 4 cosine theta, that's going to be a circle with a diameter of 4. And then 2 cosine theta is going to be a circle with diameter of 2. So that helps, just familiarity kind of thing.
If the numbers is a little more compact, would that still, like, count as correct?
I think so. Again, I think the purpose here is more for your benefit of just helping to figure out the how to set up the integral and stuff like that. So as long as you still feel like you got a good understanding of it, then yeah.
Like, that would work.
Yeah, I think so. Yeah. The one thing you want to be careful about, though, is that if this inner circle starts to like bump outside of the bigger circle, then you're going to run into some issues. You're going to think there are intersection points where there aren't, kind of thing, or something like that. So that's the only thing we'll worry about. But of course, for our purposes here, we're going to go ahead and find where these two circles intersect, or again, for what value theta. We can already see that they both intersect at the pole, but then what is that, theta value there where they intersect? Maybe from, just graphing out and doing it in your head. But we're going to solve here real quick. So let's just go ahead and do that. So we have 4 cosine theta equals 2 cosine theta. Okay. Now, how do you solve an equation like 4 cosine theta equals 2 cosine theta? Should we divide by cosine theta on both sides? No, because then you get 4 equals 2, which is like an impossible thing to solve because there's no thetas there. We're going to subtract 2 cosine theta, all right, from both sides. We get 2 cosine theta equals 0, or cosine theta equals 0. And when does cosine of theta equal 0? Yeah, pi over 2 and 3 pi over 2, right? But of course, we're only interested in that first one. We start at 0, and then at pi over 2, we make it to there, okay? And we start at 0 here, it's 4, and then we make it back to the pole at pi over 2 right there, okay? So here, we're going to use symmetry again, okay? Because this thing splits neatly in half right there. There is symmetry about theta equals 0. Okay, that polar axis right there. All right, so let's set this up. All right, if we're going to use symmetry then, our area is going to be twice 1. Oh, sorry, let me go over here. Thank you. There you go. Twice 1/2 the integral. And so what will our limits of an integration be? We're going to start our integration at what theta value? 0, right? Because that's where our curve starts right there, on the polar axis at 0. Okay? And then what will we integrate up to? Pi over 2. Exactly right, because we bring it back into the pole there. Okay? Is there a curve that is always on the outside here? 4 cosine theta. So we'll do 4 cosine theta quantity squared minus, is there one that's always on the inside? Well, it's the other one, right? 2 cosine theta squared. And then again, this whole thing here, d theta. Okay. And so that utilizes symmetry there. All right, questions on any of that? Yes, sorry, Karen, go ahead.
I'm just confused on why the balance are from 0 to pi over 2.
Why the bounds are from 0 to pi over 2? Okay.
If it was from pi over 2 to 3 pi over 2, wouldn't that be from like pi over 2 to the rotating or like 3 pi over 2? So
I see what you're saying here. Let me think. At pi over 2, we're here. Then at pi... So, I mean, pi over 2, we're here. And then at pi, we would be here. And at 3 pi over 2, we'd be back. I think if we did pi... So you're saying, why don't we do like pi over 2 to 3 pi over 2?
Yeah, I was confused on how we got our zeros, but then I realized we found this.
So we use those zeros because, the idea here is that we're going to use the symmetry to do that. So we only need to use the first 0 because at 0 we start right here, right? That's like we start, kind of like with our theta at this point, and then as we sweep around here and accumulate that area, we bring it back around into then when pi over 2 is right here. So that gives us this upper kind of like part. This upper part right here, and then we'll just double that then to get the bottom part. We don't need to worry about that 3 pi over 2, which is where they also intersect again kind of thing. We'll just double it kind of thing. Does that make sense?
So if we weren't doing like symmetry,
If we did use symmetry, okay.
would it be the integral from pi over 2 to 3 pi over 2?
If we weren't using symmetry, I think we'd be going from, it would be from 0 to pi, because we only are concerning ourselves with the, with 0. 0 brings us, 0 to pi over 2 brings us around to here, and then from pi over 2 to pi brings us back around and up to here. So we don't need to go to the 3 pi over 2. The 3 pi over 2 would bring us, would essentially, if we, so you're saying, why don't we do from like pi over 2 to 3 pi over 2? Is that what your question is?
I was just confused on like what the zeros mean.
Okay, I got you. What the zeros mean? So the zeros just mean, in this case, or like what does this mean right here? Why do the thetas, like what does theta equal pi over 2 and 3 pi over 2 mean for this? Okay, so why don't we use both of them, you're saying? I see what you're saying, as opposed to the earlier one. Okay, so in the earlier one, right here, when we didn't start at 0 because our curves didn't, I guess our region didn't start at 0. Our region started at that pi over 6, where the curves intersected. And then as you rotated around, that region ended at 5 pi over 6. You okay with that right there? So then here, right, our region, actually, if we're going to use symmetry, our region starts at 0, and then we can rotate it around to then pi over 2. So, I mean, I think, I see what you're saying here. I think you could, I wouldn't, let's see here. My hesitation about pi over 2 to 3 pi over 2, I think it's going to give you a negative value for some reason. But if you did like from negative pi over 2 around to pi over 2, I feel like that would be okay.
I was just like, I get why we're using
Yeah,
0 to
right.
0 to pi over 2 because like it makes sense we're starting at 0 and we're like rotating around, but I just don't get why we found the 0 and I'm like not using it.
Why we found these two values and we only use the one? So I think the idea is the 3 pi over 2 is another place where these things intersect. Well, let me just check here, I guess. I don't know. We'll see. Let's see what happens. So Math 9, integral from, let's see here. Let me find the actual area here. 0.5 from 0 to pi over 2. Actually, I want to do twice that, so never mind. I'll just do the integral. Of 4 cosine theta squared minus 2 cosine theta squared d theta. Okay, so using our symmetry method here, we get this. And so then you said why don't we go from pi over 2 to 3 pi over 2? And then that would be, but we'd still have the 1/2 in front because it is. Okay, so never mind. It does work. It is the same thing. So you could do it that way too. Yes. Yes. You could just use the zeros there, yes.
Can you always use the 0?
That is a good question.
I don't get how we're starting to figure it out.
Say it one more time.
I just don't understand how to find the correct balance at this point without using the 0.
So I see what you're saying. So I think, yes, you should be able to use the zeros in cases like this, again, which is just the way the graphs are intersecting. We'll see a little bit later that we're going to need, if the curves like change which one's outer and inner, then it won't be necessarily, you'll have to use some other stuff in addition to the zeros kind of thing. But when it's just a single region with one curve always being the outside, one curve always being the inside, then yes, I think you can be fine with just using the zeros. Yes, I believe so. Okay, so what I also want to do here, all right, is I want to actually like show you that we can work this out. So just in case you would need to be able to do something like this, right? The 2 times the 1/2 would simplify there. We'd end with 0 to pi over 2. We'd have 16 cosine squared theta minus 4 cosine squared theta d theta. Okay, which of course now we have like terms we can combine here. Question, Urja? Yes, we're using symmetry here. With the integral that we have set up, so ignore the 2. With the integral that we have set up here, it integrates from 0 to pi over 2. Oops, sorry, I'm off the screen. There we go. 0 to pi over 2. Yes. Where they intersect. You could have, and that was what Kara was asking too. So you could have here used, you could have gone from pi over 2 to 3 pi over 2, ignored and not done the 2, and then just done the curve. So you could have had. So this would have also been okay. What's the point? Some people it makes more sense for them to do that. Some people it makes more sense for them to do it this way. It's really a matter of personal preference, I would say. So it's going to depend on your personal preference. For me, I don't know. Maybe it's just me. Maybe I'm the only one, and maybe that's why it's confusing because I'm the only one that thinks this is a better way to do it, or not a better way, but it just makes more sense to me this way. But that being said, right? Yeah, this is fine. This also would work. Okay. Yeah, that's all. So, but this, you're saying this way makes more sense to you, though, right? Yeah. Yeah, that's fine. You can use that. Okay, it works. Okay. So, but back to this, though, right? Back to this. We can now combine like terms here. And so 16 minus 4 is 12 cosine squared theta, d theta. Okay. I guess it's supposed to be a pi over 2 there. Make sure I write that out. All right, and at this point, right, we're going to have to use that identity. Cosine squared is the 12 times 1/2 plus 1/2 cosine of 2 theta d theta. Right? Distribute the 12 then. You get 6 plus 6 cosine of 2 theta d theta. Okay? And this is where you'd want to use a u substitution. We can integrate 6, no problem, right? It's the 2 theta there. So if you let u equal 2 theta, du would be 2 d theta, and so we'd have 1/2 du. Oh, I'm going to run out of room. 1/2 du equals d theta. I'm like really writing microscopically there. There we go. Okay, so integrating the 6 would leave us with 6 theta. Integrating the cosine of u, okay, integral of cosine is sine, but we'll have the 1/2, so it's going to be 6 times 1/2 sine of 2 theta there. Okay, 0 to pi over 2. Yep. Why did I put the 1/2 in front?
Yeah.
So it's because of the 1/2 d. Like, so I'm substituting instead of d theta for this one. I'm imagining it's a 1/2 du. So there's going to be a 1/2 that goes in along with the 6 there, and then becomes sine 2 theta. I'm just skipping like the u substitution, jumping it a lot, just because I want to get through it real quick so we can move on. But yeah.
So
Okay.
how did you know to start from 0 then?
Because that's where most of our polar curves kind of start, right? Or if we look at the region here that we're creating, right? The region, we typically start with theta equal to 0, and that starts kind of like half of the region, right? And if I rotate around pi over 2, I finish off that half. So then if I just double from the 0 to pi over 2, I double it, I get the full thing. Okay, yeah, Jordan, sorry, you had a question.
So if you're saying the same thing, you said your ground is
So in this case, let's see, from 0 to pi, yes, I believe that would be, it should still work, I think, yes. In this case, yes. So let me just make sure that, let me just check that here. But yeah, yes. Okay.
Can you slide it? Just to help write a little bit.
You need the bottom piece right here?
Yeah, the area.
Okay.
No, the whole, like all the work for the area.
Oh, okay, all the work, gotcha. Right here?
Yeah.
Okay. So yeah. All right, so let's take a look here then at number 8. All right, and this one, thankfully the directions are just set up but do not evaluate. Oh, I didn't actually evaluate in this. Sorry, the final answer is 3 pi for that one, for number 7. Sorry, you should get 3 pi. 3 pi. Okay. Final answer is 3 pi. All right, so again, go on, guys, if you're right in here, go ahead and graph example 8 if you haven't already. All right, and let's... Okay, and then for cosine theta, well, we just did that one, didn't we? Okay. Just say went on, Brian, we'll move it up.
Sorry.
Oh, question, Maddie, yes. No, it's okay.
Like with the Walker method, how you could put in a point when you found the bounds in between the points, do you have to graph it in order to find which one is the outer?
No, I'd say not. I mean, I think, yeah, what you could do there, again, is like find your zeros and then pick a number in between those zeros, plug them into each curve, see which one gives you a bigger R value, which one gives you a smaller R value, kind of thing. I think that would work too, yeah. And I guess I should say, sorry, I want to be careful with that. Because if you talk about negative R values, a -4 is smaller than a -2, but a -4 would be further away. So you want to pick the one that has the R value that's further from the pole. It would put you further from the pole, that kind of thing. But yeah, that would work. All right, very good. So there's example 8. Nice little Venn diagram we've got drawn there, right? All the English teachers, all the English folks are following along now, right? We got the Venn diagram there. Okay, so let's again find our points of intersection here. So we'll set for cosine theta equal to 2. Oh, now it's when does cosine theta equal 1/2? Well, that's when theta is pi over 3 and 5 pi over 3. Okay, so we'll kind of like, there's pi over 3, and there's 5 pi over 3. Okay, and our region then, well, actually I want to hesitate about drawing that in for right now. The region is the common interior, so it is what is shared inside both curves. So it's this center kind of like, I don't even know what I would call that, but this central kind of piece right here, the overlap, right? It's the part of the Venn diagram where you would show what things are the same about those two things that you're comparing, right? So anyway, what's special about this scenario here? What's different about this than compared to the other ones? Something happens with our outer curve. It changes. Yes, exactly right. Okay. Yes, it does. All right. From 5, or from, I guess the, well, again, I'm going to want to use symmetry here, and people aren't going to be happy. But anyway, so from this part right here, right, from the 0 to the pi over 3, all right, from 0 to pi over 3, we create, it's the outer, excuse me, the outer curve is just R equals 2, right? The inner curve, there is no inner curve. It's just this wedge right here. I mean, we could literally just use the sector area formula for a circle, okay? So it's just this wedge. But then we have this teeny sliver right here that goes beyond that pi over 3. And in that case, the outer curve is the 4 cosine theta. But again, still no inner curve. Okay? So in this case, we're actually going to subtract an outer area minus an inner area. We're just going to do the area of this wedge right here. And then add to it this teeny sliver right here. Okay? And again, I'm going to utilize symmetry here just because I think it makes things easier. Now, do you need to do that? I would think no. You could probably integrate from 5 pi over 3 to pi over 3 here, and that might work. And then, well, I don't know. It would be tricky for these little slivers and things. Yes, Caitlin?
I don't understand why it would change. Wouldn't it just be, because if it's that middle part, wouldn't the outer one be R equals 2 because it's always farther away from the pole?
So let me see here if I can. So you're okay with like this wedge right here being just R equals 2. You're okay with this because again the idea is like it's like I don't want to shade this, but I'm going to have to, okay. So like this is our region, right? You're
Yeah.
okay with that being the region. Like that.
Yeah.
Okay. And so you're saying for this piece right here, which again I'm going to kind of like, for this wedge right here, the outer radius there is 2, right? You're okay with that. Okay. And then you see for this little sliver right here, you're saying you're not sure why that isn't also r equals 2?
No, I'm saying I don't understand why we have to, like, you're saying that we're gonna have to, it changes, like
The outermost curve changes,
Yeah.
yes. Yes.
I don't understand that.
Okay, so again, imagine we're rotating through here from 0, we rotate through, okay, up to angle theta pi over 3, right? The outer curve here is all determined by this curve right here of that region, right, which is the curve r equals 2. So far, so good. Then beyond pi over 3, right, that curve of r equals 2 no longer is a boundary for our region here, right? The boundary for our region changes to this inner curve right here that brings us on down to 0 once we hit that pi over 2. Do you see it now, kind of? Again, we're rotating along this point, so we're rotating along this point, and as we rotate, our r value is bringing in closer and closer and closer to the 0 there. I know, the sliver is, yeah, exactly. It's pretty crazy to see, but there it is, all right? So anyway, so the area then will be, I'm going to use symmetry, okay? I'm just going to worry about this upper half and then just double it.
So, sorry.
Go ahead, yeah. You okay.
Is it based around pi over 3, or is it based around what's farthest from the pole?
What's farthest from the pole, but it's because after pi over 3, the farthest curve from, sorry, not the curve that's farthest from the pole. So this is not outer curve minus inner curve here. This is not an outer minus inner curve here. It's not an outer minus an inner. Why? Because again, if you look here at 0, right, the outer curve we can agree is 2. You're okay with that, right? The inner curve, well, there is no inner curve. There is nothing to subtract out in this wedge here, right? The only thing that's describing that region, the curve that's describing the region is r equals 2. So you're okay with that being just r equals 2. There's no subtracting out kind of stuff, right? Okay. So then here for this region, I mean, I guess we could, if you wanted to, we could do 2 squared if we could do from pi over 3 to pi over 2, we could do 2 squared minus then this quantity, right, the inner curve right there. So we could do that if you wanted to, yes. Okay, you could say 2 squared minus this thing right here. But what you're going to end up doing, minus this thing squared as well, okay? But what you're going to end up doing is getting this curve exactly right. Like the exact curve anyway. So let me show you. What you want to do is this, right? Let me just show you what you want to do this, right? You want to do the integral from pi over 3. You want to do the integral from pi over 3 to pi over 2 of the outer curve. Let me see here. Now we want to subtract the outer curve. Let me see. That's a crazy thing. Yeah, never mind. That's not going to work the way I thought it was going to. So how can I do this? So again, it's just this little sliver you're worried about, right? That you're not sure about.
We're just, like, if we were given a problem like that, we wouldn't know what the bounds were and what's considered the outer curve.
All right, so let's just
Why
worry.
it changes and, like,
All right, let's focus on this piece right here then, right? We're integrating from 0 to pi over 3 of the 2 squared there, d theta. Right? Like that part you're okay with. And I'm doubling it because I'm only, when I go from 0 to pi over 3, I'm only getting this top piece, but I also need the bottom piece too.
Explain the bound, like the A and B.
So we start at 0 here, right? Because, I mean, at 0, we're at this point and this point.
Oh, we're doing symmetry?
Yes, we're using
Okay,
symmetry here.
that's
Yes.
why.
Yep, using symmetry. That's why I'm doubling it. Okay? So are we okay up to this point?
Yeah.
Yes? No questions up to this point. Okay. So then, after pi over 3, as we continue our rotation here, r equals 2 is no longer the outer boundary, right? From the pole outward, that is no longer the outer boundary of our region. From the pole outward, the outer boundary is determined by this curve. What is this curve for cosine theta?
It's not because it's not included in our, like, so, it's still technically, I guess, wouldn't it still technically be outer, but it's because it's not included in the shaded area, I guess you'd say.
You're talking about this piece right here.
Yes.
So we're gonna like there is no there's no subtraction here. Like here, right here, every angle theta that we had this piece. We had to take out this piece because there was like this inner white space we wanted to remove that was closer. But here, right from the pole, there is no inner white space between the pole and our region there we have to subtract out. It's just the accumulated area of that curve.
I think I get it.
Okay? So, twice, 2 times 1/2 the integral pi over 3 to pi over 2 of the 4 cosine theta squared. Okay? So like that. So there would be the integral right there. Sorry, that 2 shouldn't be right there. Like that. Okay, question, Kara?
I just, like, I understand there's that little sliver there, but I don't get how that, like, the second part of that represents.
Like this right here?
Yeah, like, I don't, because isn't it just that little sliver, like, isn't it not from pi over 3? Where's the pi over 2? Like,
So I got you. So I'll try. So you're okay with it starting at pi over 3?
I'm okay with the part in the little sliver, because I didn't even see that part.
Okay, but I mean, you're okay that the sliver starts at pi over 3.
Yeah,
You're okay with that? And you're okay with the fact that the curve that's defining that sliver, you're okay with the fact that the curve that defines that sliver is the 4 cosine theta? Okay, so then, as we rotate around with 4 cosine theta, okay, as we rotate around, that sliver ends at whenever we hit the pole here, right? Which is at pi over 2. 4 cosine theta is 0 at pi over 2. So we rotate from the pi over 3 to the pi over 2, and that brings the radius in, down to 0 at pi over 2.
So it's like another volume equation in which there's no inner bounds.
Yes, exactly. Yeah, we have to add the 2 parts together. We have to break it into 2 because the outer one changes, but the inner, well, there is no inner one to worry about, so just the curve changes.
I just never didn't see that at first. Like, if you didn't see that at first, how would you see that? Because there is no.
No, I see what you're saying. I think, that's why you want to like graph things accurately. And again, yeah, I would say graph things accurately there. As best I can say. I see what you're saying though. How would you know the sliver is there? I think the best thing to say is just graph accurately there. Yes, Kyle?
How many points will we lose on the test?
I don't know the answer to that question. It wouldn't be a ton because it's just one question. It depends if it's multiple choice or not, but at most 5, I guess I would say, kind of thing. So yeah, Urja. Without using symmetry, this one I. I mean, I think that would make it more difficult. So Urja, like for example, you could integrate from like 5 pi over 3 to pi over 3 of just the 2 squared, right? That would take care of this wedge, right? But then you'd have to add a third integral essentially. Is that what you were trying to say, Sarah, right? So you have to be 3 integrals. You'd have to do this piece, and then this piece, which is why I think symmetry is just so much easier here, right? Because this piece is determined from 3 pi over 2 to 5 pi over 3, so you'd have to do that one. Then you have to do this one from pi over 3 to pi over 2 for that piece. And then you have to do this one from, I guess you could say 5 pi over 3 to pi over 3. So I mean 3 integrals. Yes, you could. So you could. Yes, you could. You want me to write it out? No? Okay. Okay. Moving on. I'm supposed to go up through example 9. That's not going to happen, but we'll continue on here. All right. Well, you're right. Be positive. Let's see if it happens. All right. So anyway, let's graph. All right. 3 cosine of theta. So it's going to put us here, and then at pi over 3, it'll be 1.5, and then negative, like that. It's going to be like a nice circle. Hope no one has any questions on this. Well, I mean, I want to answer questions. All right. So there is 3 cosine theta, right? And so 1 plus cosine theta. Well, let's see here. At 0, 1 plus 1 makes 2. And then at pi over 2, cosine pi over 2 is 0 plus 1 is 1. So pi over 2, we're at 1. Okay, so you kind of like arc around like that. And then cosine of pi is negative 1 plus 1 will be 0. So we kind of arc around like that. And then at 3 pi over 2, cosine 3 pi over 2 is 0 plus 1 is 1. So like that. And then like that. Okay. Is there a sliver? I don't know. We'll find out. We'll find out. Okay, so this one is also asking for common interior. It is also asking for common interior here. Okay. It's also asking for common interior. Are there slivers in this one?
Yep.
Yes, there are. Okay, yes, there are. Okay, we'll see here. All right, so again, we want to figure out where these curves intersect. So we'll set 3 cosine theta equal to 1 plus cosine theta. So we get 2 cosine theta equals 1, cosine theta equals 1/2. So these intersect at pi over 3 and 5 pi over 3 again. Okay. Pi over 3 and 5 pi over 3 again. Okay. So again, we've got this kind of like there's pi over 3, there's 5 pi over 3. Okay, and the common interior, which is like that right there. Okay. Don't forget the sliver. So area, again, I'm going to use symmetry. Okay. Oh, I'm sorry, off the screen. Thanks. Okay. Let's talk about this first region here. Okay. For that first region, right, we start at 0, and we will rotate to what's our upper bound then for that first part? Pi over 3. Yeah, we're going to go to the pi over 3. Okay, and then what's our r here? The 1 plus cosine, right? This curve right here that determines that boundary is 1 plus cosine. Okay, and that's that piece plus the sliver there, right? And what curve is determining the sliver? The 3 cosine theta. And we're going to rotate from pi over 3, again I'm using symmetry here, from pi over 3 to what? Pi over 2. And again, it's the 3 cosine of theta, quantity squared d theta. Ugh, like that. Okay? Yes, Gabe?
So you're using where they equal to set up those lines and boundaries to like determine where the sliver actually is? Like,
Yes, to see it kind of like happening, right? You can see it like right here, right, and right there. You can barely see it kind of thing. It's there.
And I understand why you're starting at pi over 3, but then you go to pi over 2. Is that the origin?
So because then for that sliver, right, pi over 3 is where it starts, and then as we sweep around, because our curve is now this curve, that r changes and goes all the way down into 0 at pi over 2 is when it's happening. Okay? Yes, that's the idea.
And that boundary meets up at pi over 2, correct? As well?
The boundary,
Meets up at the origin.
yes. All right, we're going to do one more. Uno más. Uno más, por favor. All right, so inside r equals 2. Okay. Inside r equals 2, so there's our graph there. And outside, 2 minus 2 sine theta. Okay, so again, we'll start with 0. Sine of theta is 0 times 2 will be 0, so it starts at 2. So 2 towards the 0 there, right there is the first point. And then pi over 2, sine of pi over 2 is 1 times 2 is 2. 2 minus 2 is 0. So at pi over 2, we're at 0. Okay? So we're going from an r value of 2 to an r value of 0. That means we've got to decrease our r values into that point, like so. And then at pi, sine of pi is 0 times 2 is 0. 2 minus 0 is still 2. So at pi we'll be out 2 towards pi. And again, yes it is. And then 3 pi over 2, sine of 3 pi over 2 is negative 1 times negative 2 is positive 2. 2 and 2 make 4. So we'll go 1, 2, 3, 4 in that direction. And again, we're going from 2 to 4, so we're just going to expand our r values outward. And then back at the 2 pi, we're going to go right back to where we started right there. So, aww.
It looks like a pizza.
Okay. And so then we want to shade the region out inside r equals 2, outside 2 minus 2 sine theta. And so that would be that region right there. Okay. Looks like a little widow's peak or something like that. Okay. So again here, okay, this one you could kind of go either way, all right? So area equals, I'm going to use symmetry, but I'll also show you without symmetry. 2 times 1/2 the integral, okay? What, oh, I'm off screen. Darn, I keep doing that. Okay, there we go. 2 times 1/2 the integral, and what are our limits of integration going to be? 0 to pi over 2 in this case, right? Okay. There's no slivers, right? Woo, thank goodness, right? But we do have an outer and an inner. What's the outer curve? 2 squared, and the inner curve? 2 minus 2 sine theta squared d theta. Okay? There's an additional question we have to answer still, but there it is. All right, for those of you that didn't want, that don't want symmetry, 1/2 integral 0 to pi, still 2 squared minus 2 sine theta squared d theta. Okay, well, we still have to get through C and then D and example 9. So, set requests! Okay, so yes. Not you. Julia. Yes. Julia. All right, Tanto. Yep.
Right now that I'm not going to be here on Monday because I'm going to be at a college tour.
Oh, that's nice. Sorry, Kara, you too, yes?
I don't want to get behind on this test like I did the last one. So,
I understand. Any other set requests? Jordan.
so I'll do it like Tuesday.
Aubrey, yes? Are you know, you don't need a set? Okay. Anybody else set requests? Okay.
This
Yes.
is kind of in advance, but I have a stage next Friday, so I will not be here.
Very good. Well, that's exciting. So, I think, let's see here. What should we be on? Let me see. Okay, so that will be, well, we'll start into sequences and series at that point. So you just missed that. But of course, there'll be the video and, yeah. You getting this stuff okay, you think, Nick?
Yeah.
Okay.